So I believe the most recent things that we have done is talk about loops and then talk about makefiles. And I think we had gotten to the end of chapter 4, pretty close to it. Talking about for loops, the thing to remember is that with a for loop you specify your starting position, your initialization step, you specify your continuation condition, and then your update. So just like a while loop normally has those things broken into 3 separate steps. You init, your comparison or your condition, and then your update. So x is equal to 1 while x is less than or equal to 10, do something. And then you have to increment it for the update to happen. So we have several different steps going on here. One of these is the init. And I put a semicolon there. This is the continuation condition, and that's the update. A for loop just does all those at one time. For, parentheses, init, condition, update. And then with some body inside it. So, same one. For x is equal to 1 while x is less than 10 each time we increase. I'm going to go ahead and put the plus plus in front just because you can take it on faith that that runs slightly faster than x plus plus, and it's no difference if it's on a line by itself as to how it calculates. So like that, and then we could print out x there. Now there's some, we have covered for loops, yes? That's a big thumb up in the air. Dap, have we done this? Or is this new particular? Okay. So what is of perhaps interest that I don't recall us talking about is that you can leave certain things off if you don't want to have them in there. You could write a for loop that looked like this. This is assuming that x is going to be initialized somewhere else. Assuming that x has already been set, we're skipping it. That's fine. You can do that. Alrighty. What if you don't feel like doing that middle step or that last step? Assuming you are going to do the update in the loop, not in the loop header. And then somewhere down in here we have some kind of special calculation. X equals x plus y, whatever's going to update it. Some condition. If, a equals 1, then x plus plus, else x minus minus. Whatever. We might have some complex, update to x that occurs here that we wouldn't just want to express there. And we could do that. Nothing wrong with that. If you feel like being completely absurd, you could do this. Remove the condition. Well, now there's no way out of it. So you better put a break statement, right? If x is equal to 10 or whatever, break. Something like that. So, is there any reason at all to write it like this? No. That's just a while loop instead of with a different word. That is pretty much the same, whoopsie, as writing this. While true, and then having the rest of this in the braces. So do you care about doing it this way? No. I see absolutely no reason for it. But this does hammer in the fact that you can leave any one of these components off, or you can leave off any 2 of them, or you can leave off all 3. You can also initialize more than one thing at the same time. I'm just going to pop into Visual Studio. I don't see a reason to wrestle with using the command line compilation right now. Although I shouldn't rely on Visual Studio because we've already seen that it is weirdly inclusive about header files that it includes by default that we didn't expect. Well, you're just going to take forever to do that, aren't you? All right. Guess I've never used this product in this room. All right, good old boilerplate. All right, so I'm going to declare a variable. I'm going to declare a second variable. And then I'm going to write a for loop that increases one and decreases the other. For x is equal to 0, comma, y is equal to 10, semicolon. Keep running while x is less than or equal to y. And every time we update, I want to update x, and I want to decrement y. And then I may as well just see out those values. Excuse me, not using C out. We're not using C++. Printf x equals %d, y equals %d, \n, x comma y. All right. If this is large enough, you would see the point that I was trying to make, which is there we have two numbers. X is counting up, y is counting down, and it continued as long as x was less than or equal to y. And could we have written this with a while loop? Yeah, we sure could have. But the syntax would have been, would not have been nearly as concise. Now, something that was added to C++ that I don't know if it ever made it into C is the ability to define your variables right inside the for loops. And I forget if this works. I'm getting some underlines as though it's not going to. Maybe you can get away with declaring one of them but not two. All right, anyways. I'm not going to initialize them. I'm going to change that so that they're just declared like that. Okay. And these could be anything. These could be function calls. If you have some function you want to run at the beginning of the loop, it doesn't have to actually be setting a variable. It could just be a function call. And this condition could be another function call. You know, it doesn't have to be an expression like that. It could be a function call. And as long as the function returns non-zero, it's going to continue running. If the function ever returns 0, it's going to stop. And this could be a function call. Now, I'm not going to try to actually write some code that would support this, so I'm going to comment it out. But something like this: for init parentheses semicolon test semicolon update. Like that. Do something. That would work, as long as at some point test would return a false. It would return a 0. So these could be modules. Perhaps they're using some global variable to update themselves or something like that. But that works. You can put updates to the variables in the test expression themselves if you wanted to. Every time we go into here, I want to increment y or x by something. I would not ever do that. I would put my updates in a separate step in here or down in the body, not in the test. Okay, so that's one kind of loop. I do not believe that we talked about do loops. Correct me if I'm wrong. Did we talk about do loops?
No.
Okay. Do loops are available in some languages. They're not available in others. For example, Python does not have a do loop. A while loop is a pretest loop. And so is the for loop. While loops and for loops are pretests, meaning that the condition is evaluated first, before the body. A do loop, different. It's post-test. The condition is evaluated after the body. So you could have this. Int x is equal to 0 while x is less than 10. Printf x. Printf %d \n, comma x. And then we'd have to update x. This test happens before it goes in here. So if this was set to some invalid value like that, it wouldn't go in here at all. And that's probably what we want. Maybe we don't want x to go in there. I mean, maybe we don't want to execute this value. A while and an if statement are kind of synonymous in this case, because if this is false, then it doesn't evaluate that at all. So the above body would not be performed since the condition is false. What if we write it as a do loop? Int y is equal to 0. Do some stuff. Printf %d \n end quote comma y. And then increment y. Do that while y is less than 10. Now, if this had started off at 0 and the other one started off at 0, they would do the same thing. This would print if x starts off at 0. This would print 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If x starts off as 10 or above, it prints nothing. So if x starts off at 20, nothing gets printed. But this way, yeah, starting off at 0, if y starts off at 0, it behaves the way we would expect. Prints a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this final time, y gets incremented to be 10. It is no longer less than 10, and it bails out of the loop. So that's just like the while loop did. But if y starts off at 10 or more, the body gets executed anyways. So if y starts at 20, it would print 20. Right? If this is y is equal to 20, do this stuff. Print 20. Okay. Add 1 to it. It's now equal to 21. Is 21 less than 10? No, it's not. So it stops. Whereas on the other one, if it was 20, it didn't go in the first place. So the key thing to remember is that with a post-test loop, the do loop, the body gets executed no matter what, at least one time. With a pretest loop, the body may not be executed if the condition starts off false. So the body gets executed no matter what at least one time, even if the condition is false. Because the condition is checked second, post-test, second. Pre-test means it happens before. Are there a lot of times when it's better to use a while than a do? I'm sure that there are good. You can almost write everything either way.
So if you have a do, you have to have a while at the end of it?
Exactly, exactly.
I feel like I should do that for the homework, but I didn't know how to use a do, so I used like 5 whiles or something.
Yeah, that's fine, that's fine. That's fine. I wasn't expecting you to use do loops. I mean, let's play with this. Do print f %d \n. Let's print out x, and then let's not put a while clause there. Yeah, it absolutely depends on the while. Some languages, not this one, not when, while, you know, something. While x is greater than 0. Let's subtract 1 from x every single time just so that it'll go in this loop. Okay. All right. So whatever x was here, it's going to get printed out a second time here, and then we're going to start decrementing. And as long as it's greater than 1, it's going to keep going. But if it's ever not greater than 1, it's going to stop. Yeah, so by the time we got here, x was equal to 6. Why was it 6 rather than 5? The last time we printed it, it was 5. Right? Here, we printed it, it was 5. But then all of a sudden, when we get down here, it's 6. Why is that?
Was it incremented after the print?
Exactly, because it incremented it before it figured out it was false. So by the time we drop out of here, it's equal to 6. So we print it out, and we start subtracting 1 from it. And it counts down to 2, meaning that by the time we get here, it's now equal to 1. Some languages have a do until statement, but not C. Do this stuff until x equals 1, something like that. I kind of like that idea. I almost like that better than do while, but doesn't have it. This will just repeat until this condition was true. This one repeats while the condition is true. That's the only difference. So your general rules of thumb about when to use which one is if the loop body has to be executed at least one time, for the code to work, use a post-test loop. If you are counting over a range of values, use a for loop. Otherwise, use a while loop. And can you jigger a for loop to behave exactly like a while loop? Yeah, you sure can. I just use for loops almost as a matter of course, unless it's that one case that I showed you, where it's just the same as a while true. I won't write that as a for loop. But that's my preferred loop. That's what I always go to. We did mention break and continue, I hope. Did we talk about break and continue?
I don't think we talked about continue.
All right, let's. Okay. Break causes control to exit, to skip the rest of the loop. Okay, that's a stupid way to word it. Break will break out of the loop, skipping to the statement after the closing brace. So while x is less than 10, but if in somewhere in here we put if plus plus x is equal to 4, break, it'll bail out immediately. It won't continue to go. How about continue? Continue almost does the same thing, but instead of breaking out, it forces it to jump back up to the condition. So like this, while x is less than 10. And then say we did something. X plus plus, you know, and then we print fx. And then we have some kind of if statement in here. If x is equal to 5, then continue. Then we had some more stuff in here. Print. Neato. Whatever. Okay, so what's going on here is that it would do that, it would do that. If this wasn't true, fine, it's going to go ahead and print neato. Then it's going to come back up here. In fact, why don't we code this so that we can actually watch it? But eventually, x is going to equal 5, and it's not going to print neato. It's going to jump back up here. It skips the rest of the block. So it skips the rest of the body, and processing jumps back to the condition. So break causes it to bail out of the loop. Break causes it to repeat the loop by going back and testing the condition again. Now if the condition is false, it's still going to bail. So let's do one more loop. We're going to set x equal to 0 and we're going to count it up. Doesn't matter what kind of loop. Since it doesn't matter what kind of loop, let's just use a for loop. X is equal to 0, x is less than or equal to 10, x plus plus. In here, we're going to check this out. We're going to do printf, question mark, just for funsies. Then we're going to check. If x is equal to 7, we're going to break. If x is equal to 4, we're going to continue. And then we're just going to print the number out. Right, this output's not going to be that impressive. But what we're going to see is that it's going to skip printing the number 4. Why is that? Because when it's running down here and it hits continue, it's not going to get to execute that statement. It's going to run back up here, x is going to be incremented, and then it's going to go on its way. So it'll count 0, 1, 2, 3, 4. Well, it won't get to 4. It'll count 0, 1, 2, 3. It's going to skip 4 because of that. And then it's going to print out 5, 6. It's not going to print 7 because the 7 is our break. Like that. 0, 1, 2, 3, 2 question marks because it did get that far before it checked to see if it was 4. So it skipped printing out the 4. It did the 5. It did the 6. And then when it got to 7, it stopped. So break causes early termination of the loop, regardless of what the condition is, and continue causes the loop to repeat right then and there, skipping the rest of the body. So what could you use that for? My favorite way of doing a loop that's supposed to exit until the user wants to stop is as a while true loop. And I'll show you what I mean by that. Something like this. While true. That's just a loop that should run forever. It should be an infinite loop. except we don't have the true word. While 1. That's the same thing expressed in C terms. Okay, so let's ask the user, enter a test score, or -1 to quit. Let's get that value, int score, and let's read it in. Scanf, %d, end quote, ampersand score. And then we're going to test it. Because if they did enter a -1, we don't want to do anything. We want to stop. So if score is, in fact, equal -1, then break. And then let's just print a message. Test score, entered, %d, \n, comma score. And if we were cool, we'd be keeping track. We'd have a total, you know, an accumulator, and we could calculate the average and stuff like that. But this should be enough to prove the point. This will let us enter a series of numbers, but if they ever enter a -1, which is the sentinel value, then it'll stop processing at that. And can you do the same thing without using a break? Yeah, we could rewrite this so that it doesn't use a break. And the books won't show you writing it like this. The books show using a priming read in order to accomplish this. I'll show you the difference between that. I'm not sure I've mentioned that. Probably not, since we haven't talked about break very much. Oh, I need to add the warning. Alrighty, somebody remind me of the pragma. Pragma, ignore warning.
It's warning, disable.
Warning : disable. Here, I'll look it up.
No, it's a parentheses, and then disable : 4996.
Thanks.
You have a colon here.
Need a colon there?
Yeah.
All right. Yeah. All right. So enter a test score, 100, 200, whatever. Eventually, I'm going to get tired, and I'm going to hit -1. Press any key to continue. I'll show you why I prefer to do it that way rather than what the textbooks usually show, which is using a priming read. Here's how the textbooks usually do it. I'm going to declare my score variable outside, and then I'm going to ask for the test score. I'm going to just cheat and copy and paste some stuff. So we ask for the score, we read the score in, and then we enter our while loop. While score is not equal, !1. In the loop, I'm going to go ahead and print my test score entered message. And then I'm going to repeat these two steps, the printf and the scanf. Okay, so these two chunks of code are functionally equivalent. They do the same thing. Here's what I don't like about this second way. This is known as the priming read, by the way. The priming read is the input that's gathered before the while loop in order for the to allow entry into the while loop. And so we have the read here, and then we have a second read here. We have duplicated code. You know, I essentially did, you just saw me, I copied and pasted the output and the input statements so that they are repeated a second time. Conceptually, I dislike that significantly. I would rather just have the input done in one place so that if I ever have to change that, I only have to change it in one place. This does introduce a bit of logical complexity because it requires that check, that if statement. And you can do the same thing without a break statement, and you can still avoid, you know, your priming read, but to me this makes sense. You'll eventually pick a style that you're comfortable with and go for it. And this is in fact what just about every textbook I've ever programmed or written from, taught from, shows doing it that way. So this is the priming read, and then the successive reads are done inside the loop. Wrong. Right. All right, so when it says a counting program that starts from 1 to 100, when I uploaded the instruction as a separate Word document, I made it 5 to 100, right? And this one shouldn't be from 100 to 1, it should be from 100 to 0.
Oh, I already gave you mine.
You don't have to modify it.
Okay.
It's fine. It's
yeah,
fine.
It just stops at like 6 or something.
Yeah, that's cool. That's cool. So the looping structures use conditional expressions, the continuation condition, to evaluate how many times something happens. It repeats a body of code. The body of code can just be one statement. If it's more than one statement, you have to use the curly braces. Plus plus is useful for incrementing the counter. Or if you wish, you can decrement it. You can also, of course, increment or decrement by things other than 1, in which case you use plus equals 10 or minus equals 5 or whatever. The increment and decrement can be placed on either side of the variable, which produces different results. We've talked about this. If the plus plus happens before the variable name, it means update it instantly at that moment before doing anything else in the statement. If it follows the variable, it means use that value, perform the rest of the statement, and then add 1 to the value. And so plus equal and minus equal and times equal and, divide equal, just perform, that operation that's specified on it. A minus equals 10 subtracts 10 from it. So the loop's beginning and ending braces are required only when more than one statement is the body. However, I think you ought to go ahead and just do them anyways, unless you just think it makes the code cleaner not to. An infinite loop is one when the loop's expression is never set to exit the loop, when the test expression never becomes 0, when it never becomes false. That's why this would be an infinite loop. Nope, nope, nope. That would be an infinite loop without the break statement, because there's no possible way for this expression to ever become false. So the do loop is at the bottom of the loop rather than the top. So that's called a post test. And the for loop is common for building loops where the number of iterations is already known or can be known prior to execution. Counting loops, that kind of thing. When executed, the break statement terminates the loop's execution and returns program control to the statement following the end of the loop. The continue statement skips over the remaining statements in the loop body and continues in the next iteration of the loop. I like the way that's worded. I'm going to nab that one. I think I'll just leave that one alone now. And the system function. Can be used to call operating system commands, which is great and all that, but if you're using Windows, then it's going to behave differently than if you're using Bash, you know, on Linux or on the Mac or whatever. So they give several examples in the textbook, and we're probably not going to do very many of them. But we do have our pause command under Windows, and you have the clear command, which you could use on Linux or in Windows, except it's not clear, it's CLS. They couldn't even come up. Microsoft is such an odd beast. Alright, so that's the end of chapter 4. Since I made a few changes, I need to remember to upload the changes. I modified the Makefiles page because you asked the question and it wasn't in the PowerPoint. How do you exit? Can you only have one Makefile in the directory? And the answer is no. You can have a lot of Makefiles in it. You just have to specify which one is running.
So, like, I never got to quite understand the point of the Makefile. Is that like if you're just working on a really big project?
Exactly, because you know the simple things that we write in these classes are just like 1 or 2 or 3 C files, but you could easily come up with one that had 70 C files in it.
Okay.
And in that case, just being able to run make and let it figure out which files have changed and recompile only those and then link it together is way, way, way easier than you recompiling every single one. Because you could write a script, you know, that would call GCC against all of them. But then, you know, if it's a really large project, it could take a long time to compile if it had to recompile every single file. And this one would just let you conditionally do the ones that have been touched.
Because I've installed like stuff before, and sometimes you have to use make to install it. So
oh, really?
Yeah. Like let's say you'll get like a tarball or something like that.
Oh, yeah.
And sometimes you have to do that.
Okay.
Instead of if it's not in the package. It just.
Well, that's interesting.
Yeah.
But yeah, that's why you use a Makefile, is to simplify the process. That's interesting. I didn't know installers were using make. That's pretty cool. So make by default will use any file called Makefile in the current folder. So you better have one or else it'll error out. But you can specify a different one with the -f parameter. Make my file too. So since we illustrated using a clean option, you know, I want to delete everything. Am I not going to find one instantly? Like that. So if I type make space clean, it'll remove the executable. I would have to do make -f file name space clean. So the file name comes first, and then you could put in the additional make parameter that you wanted, you know, to trigger your target. So that was the only page that added on that one. All right. Now this only actually has the bare bones beginning of chapter 5. So we're going to branch off and start doing something different. But what the textbook is talking about, and this is not under testing conditions, this is blackboxing, encapsulating. Information hiding. Information hiding is the concept when you conceal the implementation details in functions. The functions are black boxes. You don't know how they're working. You just know that you can call it and have it magically work. So it's a component that performs a task. You don't have to know how it works. The task just simply happens when you need it to happen. So for example, we have no idea how printf actually does its business. We just know that we can invoke it and that some good stuff happens. Same for scanf. We understand that if we call it and we pass in, you know, a pointer to a variable, it'll fill in the variable according to the formatting string, but we don't know how it works. So for example, we get given a lot of functions that we can use to test character values. Is something a digit? Is something lowercase? Is something uppercase? That way we don't have to write our own functions that do if ch greater than ASCII value capital A and ch less than ASCII value smaller z or something like that. We don't have to write those. And even if we did have to write them, it would be a good idea to stick them inside their own functions so that we could ignore the details about how that happens. So prototypes, which we've talked about. The function prototype tells C, the compiler, important information about it. The definition type and any parameter types that need to be passed into it. So the data type returned by the function is the one that precedes it. If it's not going to return anything, you declare it as void. And then the number of the parameters received and their types is specified in the parentheses. I like to put my own variable names in there as well, but they're not strictly necessary for a prototype. Now as you get to other languages, you'll see all sorts of weirdness where you can do things that are called named parameters. C does not support named parameters. I don't recall if it supports default values for parameters. Let's find out. I'm going to go and I'm going to write a little function just to test out the idea of a default parameter. I'm just going to write one called void test int x, but I'm going to try to default x to the value of 1. I'm seeing an error already. Printf, okay, %d \n, comma x. It's not liking that. Nope, no default values in this language. One thing you can do though is you can specify that it should not be able to change x. Now, why you would think that you needed to declare that, I'm not coming up with a real great answer for that, because any changes to x are not going to modify the contents of your variables anyways. If you do this, int a is equal to 30, and then you call test with a, and that word const isn't in here, then that says we're free to change that. You know, we could change that to 40. But then if we printed it out, whoops, excuse me. If we print this out, we're going to see that it's 40, but by the time we get out and we print it out here, it's still going to be 30. That should have been an x. Okay. So why did that happen? Because C is doing pass by value, pass by copy. The value of A is what gets copied into X. And this is just a variable that's defined to accept a copy of whatever's passed into it. It is not this variable. These are not thematically united. That's called pass by reference. And C does not support that. I say with some trepidation. Could be that a recent update has modified it to do so. But without doing any special syntax, it's going to always do pass by copy. If we wanted this function to be able to change the value of this parameter, and for him to know about it, we could do one of two things. One is that we could pass the new value back, in which case it would look something like this. If we declared him as an int, and then we returned x out of him, then if we did something like this, great. Now when it runs, it's going to print 40 and it's going to print 40 there. And you know, we got our test value back, or we got our modified value back. That's one way to do it. The other way is to pass it in as a pointer. If we pass it in as a pointer, we can change it. Okay, so with that in mind, and I'm going to undo these recent changes. If I declare this as a const, it won't let me modify it. It makes sense, but Not coming up with a good reason to declare my parameters as const. It does make the compiler tell you if it's supposed to change, and I guess you could just do it as a matter of course. You know, you could define every one of your function parameters as const and just be happy with that.
So you said before, when it's const, like the compiler just checks if you change it and it will like give you a warning or something?
It gives you a compilation error. You see it's underlining it right here. If I try to build it, it's just flat out going to not compile. That's what the const keyword does, is it stops the compiler from allowing your code to do that. And if you've used a language without the ability to define constants like Python, then that is something slightly new.
Well, we didn't even have a compiler there.
Right, but I mean, you could still get syntax errors out of it. But there was no way to define a constant in Python. So you just had a gentleman's agreement, which is that if you declared a variable as being in uppercase letters, you knew that you were supposed to treat it like it was a constant. You weren't supposed to make any changes to it. So that's all the constant keyword does. It doesn't really make the data safer somehow, you know, from external prying or whatever. It just stops you from making mistakes, from changing values that you don't want changed. Or even more so, stopping other programmers who get into your code from making changes, you know. And when I mean get into your code, I don't mean they hacked into it. It's just their job to make modifications to your code. So if it was really important that once passed in, like this was some kind of size limit, and that limit had better not be increased halfway down because the array was dedicated, you know, only out to a certain limit, then it would make sense to put it as a const. And I'm sort of contemplating the idea of just putting const on all of them as a general matter of course. But for now, I'm going to get rid of that. We know that even though it's not defined as const, that any changes to it here do not take place here. But what if it is passed in as a pointer? Then you can change it. So void test2 int star px. We're going to pass in a pointer to an int rather than that value itself. And so now if we type in star px is equal to 40, and then we call test2 passing in the address of A, and then we print it out, it is going to say that it's 40. So this actually did change it, and it doesn't matter whether this is const or not, because it's not changing the value. Oh, well, what do you know? Make a liar out of me. All right, now that kind of makes sense to me in a way.
So wait, you said before that the pointer is just like where the memory of that is?
Right.
So
The pointer points to whichever byte in your computer's RAM that variable is held at.
I mean, I guess if it doesn't change, it makes sense. Like if the place where it's stored doesn't change, I guess that makes sense.
But I wasn't changing the value of px. I was trying to change the memory
Yeah, but
that px pointed to.
Yeah, if you say like that's where they store the value, then I guess you can't change where.
Yeah.
Yeah, it makes sense, I guess.
What's bugging me about it is that C++ distinguishes the idea behind a constant pointer into a pointer to a const, if that makes sense. And this is flagging an error like it's a pointer to a const, something that you would not want changed. Can we even use that variable in this case? Could I print it out at least? And the answer is probably yeah, you just can't change it. Okay, all right. So now putting const on my parameters begins to make a little bit more sense to me, because if you're passing pointers around, maybe you don't want to, maybe you want to insist that it can use that, but it can't change it. And so that actually seems like a good use of it to me. But going back to where I was, if I change x to something else now, I would have to change it based on using its address. So in general, I always declare my pointers with a p variable to indicate that it's a p. And then I just pretty much know that if I'm going to dereference it to get a hold of its memory, to access it that way, then I have to do star p. And if it was a pointer to a pointer, which you can actually have, then it would be star star pp. And if it was a pointer to a pointer to a pointer, which you can actually have, then it would be star star pp. Now, why would you have a pointer to a pointer? What if it needed to change not only the contents of that memory, but the pointer itself, right? It needed to relocate it so that it was pointing to a new memory address and not merely change the contents of that memory address. Then you'd pass in a pointer to a pointer.
This is kind of off topic, but you know how before you were explaining like the compiler turns your code into machine code?
Right, it turns it into object code, machine code, right.
So I knew like a lot of people complain that they don't have source code, but can't you just get like some like a decompiler?
Yeah, you can get a decompiler and run a decompiler on a .exe or against .obj files, and it will regenerate source code. Maybe. It's possible to have executables that were not compiled, right? That were created, using an assembler instead. In which case, you could have code that could not be reverse compiled into C if they follow programming structures that C doesn't follow. But in general, yeah. The thing about that is that when it comes in, it's going to be difficult to read. It's not going to have usable variable names. The functions are not going to be usable function names. It's just going to be like, variable A1, A2, A3, because there's no way that it would know what variable names the programmer used.
That's weird.
Yeah, you're just getting pure logic. Now, if it was compiled for debug release, then a lot of that information is in there. And so if you ship out code that was compiled in debug mode, then it will have all those variable names in there. And it'll be remarkably easy for somebody to decompile it and figure out what it's doing. So
I guess they don't want you to do that. They just won't do it.
Right, they would compile it as release. Oh. Right. We ought to, good little project. Find a decompiler and decompile one of your executables that you write in this class, just to see what happens.
Do you think if it was just in release, it wouldn't have your comments in there too?
Comments are removed no matter what.
Okay, so that's weird.
Because they're completely ignored in the generation of the binary of the machine language. Yeah. But so are variable names. All we have are memory addresses, and it's a compiler's job to turn all your variables just into symbolic memory addresses. So it is not always necessary to send input. So the function may be defined without any parameters. It is not always necessary to return data from it. So in that kind of case, you would say that the function is void of parameters. I don't like the use of the word void there because that makes it sound like you stick the void between the parentheses, and you don't. You just don't put anything between the parentheses. And or are void of a return value. Now, if it's defined as void, you can leave the return keyword off entirely. I like putting the return keyword in there, but then if you're using some compilers, it gives you a warning that it's a unnecessary return, which really bugs me. So the variable scope identifies and determines the lifespan of any variable in the programming language. When a variable loses scope, it means its data value is lost. Two types in C, local and global. Local variables are the ones that are defined inside the functions. They lose their scope each time the function is executed. I would say exited. That's just a copy and paste of the book, but I would say exited. So for example, up here, if I declare a new variable in my code, int Fred is equal to 5, I can't get a hold of Fred down here, even after I've run it. So if I invoke Fred2, or excuse me, if I invoke test2, that doesn't mean that all of a sudden I can do anything like print out the value of Fred. And the reason why is that this variable is only valid for the scope, the block in which it is defined, or any nested blocks within it. Once it comes out of here, it is out of scope. You can't get to it. Now you could return it if you wanted you to, or you could set that value, using a pointer, but the variable itself disappears. So that's local scope. And then there's global scope, which is where you declare a variable outside of any of your functions. And now this is available to every one of these functions. If I want to print out Fred, I can do so. So before I call test2, I'm going to set Fred equal to 100. But then while it's in test2, it's going to set Fred equal to 6. And so when it's done executing and we print Fred, we'll see that it's x is equal to 6. All right, so Fred is 6. So that's global scope. And it's generally frowned upon. But the problem is that in the other languages, C++ and things like that, it makes it real easy to write your code in terms of classes. And you define your variables as being class members, which is effectively a global variable that's just tucked away in a nice class definition. And we don't quite have that option in C. We're not defining classes, and so we can't just make things class variables and then pretend that we had no global data going on. But there are good reasons not to use global variables. I hope that the book yells them out because I'm not coming up with the instant, snappy reason for that. But then you get into a problem of how do you access that global variable from another .c file? I have this variable Fred over here, and which, by the way, just for my own personal purposes, I always prefix the name of a global variable with G underscore. Just so that when I'm looking at the code and I see something like print out G underscore Fred, I know that G underscore Fred is a global variable.
Oh, what happens if you have a global variable and then inside a function you change it? After the function ends, does it go back to
Nope, it is changed. Okay. That's the entire point of using global variables, is so that the data is not lost the way that it is with a local variable. Right? Because when we were calling test A, it was setting A equal to 40, but by the time we got back here, this was still 30. Because that parameter is not equal to this variable. It's just a copy of it. But in this case, Fred is only one memory address, and everywhere we use it, it's all pointing to the same address. So any change to it is just, that's it. Does that make sense?
Yeah.
Yeah, so that's why you use them, is so that you could have a global variable and you can have a whole bunch of functions that depend upon that global data set. What if we need to add another file that is going to use that global variable? So I'm going to create another .c file. And then I'm going to go in and I'm going to try to access Fred. That's not right. Okay. Void print Fred. And what do we want that to do? We want it to print f Fred equals %d. Now it doesn't know what Fred is.
Don't you have to include the C file?
No, if we include the file, it would bring in the entire contents of it. What we want to do is we want to define it as an extern. Extern int G underscore Fred. Oh, well, for one thing, I wasn't calling it the right thing. That was not a very good example if I had that wrong. And you better not work, Microsoft C. Okay, there you go. Yeah, still undefined identifier. So what we would do is, here's what you would not do. Int g underscore Fred is equal to 0. That would make this error look like it was gone. But if we actually try to run it, if we actually try to build it, compilation works, but the linking fails. I thought I typed # include. And the reason it fails to link is because that variable is already defined somewhere else. We have two variables with the same name, two global variables with the same name. And we also saw this error when I had us put a variable in a .h file. And then when that .h file was being included in two different programs, then we wound up with two different global variables with the same name. So instead, what you do is you declare it as an extern. Or not. It's going to be that way. Oh, well. No, I'm not getting why it's complaining about that.
Are you supposed to still be setting Fred to 0?
Oh, you're right. I should not be setting it. Please be the answer. Thank you. All right. So what this is doing is it's telling the compiler, yo, I need to be using a variable called gfred, but it is not defined within me. But go ahead and create all the code as though I have, as though such a variable exists. And then it's up to the linker that runs after compilation is done to produce the executable that goes, oh, well, this is really a variable that's defined in another file, and I'm going to substitute the address and stitch it together so that it all works appropriately.
So when you have multiple C files in Visual Studio, it just automatically links them?
Right. Visual Studio is behind the scenes making its own fancy make files and all of that stuff is being linked together. And if we start using Eclipse, it does the same thing. It's not magical of Microsoft to do that. Okay, I want to veer off slightly. Well, let's go ahead and look at the rest of the PowerPoint, all the next 2 pages. So this is a local scope variable, meaning that whatever value you store in it is going to be lost unless you've set it, in a pointer or returned it or something. But global scope, you use them when you need to share data between functions. So to support the concept of sharing data, you can create and use global variables. They're created and defined outside of any function, including the main function. Yeah, and it says examine the next program. That doesn't work because the next program isn't here. But I will put in the code that we just defined, that we wrote here. And then we'll make comment how you use it to access a global variable from another file. Define it as an extern. Okay. Although we haven't hit it in the book yet, I've never shied away from throwing material at us that isn't in the book, which is, in the specific chapter we are in, the idea of a struct. If you've done Java or any of those other languages, you know that you have the idea of a class. And you could declare a class like this. I have a patient, and the patient has a first name, the patient has a last name, the patient has a birth date, they might have an age, and that kind of stuff. And then, as part of that patient, as part of that class, you can also throw in some functions, which are called methods when you're doing object-oriented programming and you're attaching functions to a class. C doesn't have classes at all. So what it does have is a predecessor of classes called structures. A structure is a data-only class. So we could do this, struct patient, and we could list what the patient's got in it. Let's play with that just a little bit. Let's go back to main, and if you feel like doing this with me, that's totally cool. If you just want to watch, that's also totally cool. I'm going to declare a structure. Struct book, and the author of the book, or first the title of the book, we're going to have space for 20 characters in it. And then we're going to have the author of the book, and then we're going to have the publisher. So these are character arrays. These are the more primitive ways of doing string handling than we had in Python or Java or C++. So I'm going to create a book. I'm going to copy and paste that above main so that it's there right here, so that as I'm looking at the code I can compare it. So struct book B1 is equal to, and I'm going to fill in that book with some information. The Stand by Stephen King, published by Doubleday or whoever. So what we've been doing up till now is each variable has held one piece of data. Now we've created a variable that holds several pieces of data. And by the way, this is a difference between C and C++, is that in C++ you would just define it like that. You don't have to use the word struct there. It just assumes it's a structure or that it's a class. But in C you do have to have the struct keyword there. So how about let's define another structure that holds a fraction. And it's going to have a numerator and a denominator. So int numerator, int denominator. Now I'm going to create a fraction. Same way. Struct fraction f1 is equal to 1, 2. So after this runs, B1's title is The Stand, B1's author is Stephen King, and B1's publisher is Doubleday. After this happens, the numerator for object F for structure F1 will be 1. The denominator, but we could create more than one fraction. Struct fraction F2. You know, this one is going to be 5/7, like that. Let's write a little function that will print out the value of that fraction as a decimal value. So void print, or heck, we could calculate it and we could return the value. Yeah, let's just print it. Print fraction. It's going to take a fraction as a parameter. I'm just going to call it f. Now let's get the data out of it so that we can reference it. And I'm going to cast it to being a double so that you know, if it's 1 divided by 2, we actually get 0.5 rather than 1 divided by 2 integer math being 0. So that's the numerator. So I'm is equal to f dot numerator. Nope. Oh, come on. And then double D is equal to f dot denominator. And then double the result is equal to n divided by d. And let's print that out. Printf fraction equals percent dot 4f. We're going to print it out to 4 decimal places. Backslash n, and let's print out the result. That should have been a comma. So down here, I'm going to print out the 2 fractions that I just created. Print fraction, and I'm going to pass in fraction f1. And in print fraction, I'm going to pass in f2. And so 1 divided by 2 is 0.5, and 5 divided by 7 is about 0.7143. So I hope you can kind of see the utility of having structures. Structures are cool ways to pass around groups of data. Now that doesn't mean that you need to declare every single variable your program can use in one megastructure. Your structure should be concise and hold only data applicable to, you know, a book or a fraction. You know, if you have a different set of information about publishers or your inventory, well, your inventory may hold books, but you're not going to be putting additional inventory information in that book structure. So source 2 has something called printfred. But I don't have anything over here calling printfred, I don't think. If I try to access it, if I do up here, printfred, it doesn't know what printfred is, so it should not compile. Oh, and make a liar out of me and just work perfectly. Why don't you? Let's rebuild it. Okay, even if it doesn't come up with an error. Okay, here it says, warning, printfred undefined, assuming an extern returning an int. Well, Fred isn't returning anything. It's declaring void. So for this to successfully file and compile, and it should call it an error rather than a warning in my opinion. They're being generous there. For us to be able to invoke printfred, this code has to know what printfred is, what kind of data it passes back, and what it takes as parameters. And so that's why you prototype it out. Void printfred, like that. And you're just saying, well, I need you to know that there's a function called printfred somewhere. And you need to know that information so that you know how to write code around it, Mr. Compiler. Without that, it won't know. And so the times when you use prototypes are when the functions are defined in other files, as is in the case here, or when the functions are declared below where you're going to call them. Because otherwise you have to declare all your functions above where you're going to access them and in the same .cpp file. Excuse me, in the same .c file. So typically what you do is you throw your externs and your prototypes in the .h file so that you can include them by all the .c files in your project.
I see, yes.
Maybe worth lecturing about again. We just did it for the first time this time.
It seems like a lot of work when you could just put them all in the .h.
Yeah, but then if you include that .h file in more than one file, you have multiple definitions of those functions.
Oh, and it won't let you do that.
Right, exactly. Right, exactly. Yeah, you could write an entire program and then cut it and paste it into a header file, and then your program just says # include my program. And it would still compile. But, to make useful header files that could be shared between more than one .c file, that would be the problem. Okay, does that homework make any sense? Dig into it a little bit so that we can look at it again on Wednesday. On Wednesday, we'll do more lecturing over that, and we'll be preparing mentally for the exam, which will be on Monday. And so it looks like we'll say that anything from chapters 1 through 4 and from our Makefile lecture, not that I'm going to make you write a whole great big Makefile on the fly, and our preprocessor lecture will be available for testing. But all that information sitting there inside the PowerPoints, right? If you got stuff, you could just Google them up, or just take a look right there. Okay, let's make a Dropbox and we will call ourselves done for the day.